So for stoichiometry unit, we've been running a lot of numbers, but that's not really chemistry. We have to visualize what's going on. And so I'm going to talk about what a reaction looks like. And here is hydrogen with oxygen making water. First common mistakes I see is people say that's hydrogen, and then they say that's hydrogen. But hydrogen is two hydrogen atoms, and they have to be bonded, okay? And this says that I have two of them, okay? And then it's going to react with one oxygen. And then what is going to happen? Well, these bonds are going to break, and they're going to rearrange, and I'm going to form two waters. And you'll notice that this is an absolutely perfect reaction because I have nothing left over in the beaker. Okay, so I had two hydrogen molecules or 2 moles of hydrogen and a mole of oxygen. I made 2 moles of water. And so we're starting out on limiting reactants. Let's see what that looks like. Here I have 2 hydrogens. Okay, oops, that's not right. And let's say that I have 3 oxygens. Okay, so now I don't have that perfect stoichiometric reaction that we had been doing. We're going to have some leftovers. Okay, so my hydrogens break apart and my oxygen breaks apart and we reform water. And then I can't make any more water. Well, why can't I make more water? Because there's no more hydrogen to mix with these oxygens. So what's left in my beaker when the reaction is completely done is 2 moles of water, and I still have an excess of 2 moles of oxygen. So this was my excess reactant, and this one ran out. This is my limiting reactant. And we calculate everything based on this amount in moles because that's the one that predicts how much is made. Notice I can't make any more. So this amount predicts how much product can be made. It also predicted how much oxygen I use. So what we can look at this as a reaction is before is what I started with, and I put in 2 moles of hydrogen, and I put in 3 moles of oxygen, and I had 0 moles of products. Why? It's before the reaction happens, so there are no products before the reaction happens, and I can write 2 moles here, and I can write 3 moles here, and now you see that I have my limiting reactant problem. So let's see what happens, what changes, and what's left after. So the first thing I do is I'm going to use up all 2 moles of my hydrogen. Okay. I used up all 2 moles. That's gone. Now, how many moles of oxygen was used up? Well, I used up 2 moles of this, and I used up only 1 mole of this. Okay, and you can see that I made 2 moles of water. Okay, so that's what happened in my reaction. So after the reaction's done, what's left in my beaker? Well, I have 0 moles of hydrogen, I have 2 moles of oxygen, and I have 2 moles of water. And so whatever ran out is my limiting reactant. And this is what you need to use to calculate everything. Let me show you how that works. If I start with 2 moles of hydrogen, and what this does is it calculates the change line, okay? So I start with 2 moles of hydrogen. Whoops. And I need to figure out how much oxygen I'm going to use. So I put oxygen on top, my hydrogen goes on the bottom, they go away. This is my mole ratio. It's a 1:2 ratio, and that gives me 1 mole of oxygen will be used with 2 moles of hydrogen. Okay, we already knew this was a limiting reactant. So we use that to calculate it, or if you don't know, you pick one and you see, I'm going to use 1 mole of oxygen. Did I have enough oxygen? I certainly did have enough oxygen, and so that is going to be my excess reactant. Okay, and that is what we're working on today. So this BCA chart tells you before, this is what I have. What's changing? 2 moles are going away of hydrogen, 1 mole is going away of oxygen, and 2 moles are forming on my product side, which is for the water, and after is just what's left in that beaker. Okay. So we're going to use these BCA charts to determine our problems with limiting reactants. And so here are our notes. This is how we try and think more qualitatively of what's actually happening in that beaker. The first thing to know is this is a BCA chart. Before the reaction happens, what changes are occurring, what's disappearing and what's appearing, and then after the reaction, what's left in the beaker. The most important thing to know is only moles go in here. So let me show you what that is about. Basically, we're going to convert everything to moles, and this is where our BCA chart goes, and that's why we use the mole ratios to configure everything in our BCA chart, and then it might ask you to convert what's left to here, and we'll see that in a minute. So this makes things faster, and it makes it it helps you understand it better, okay, than just running math numbers. Math numbers is a way just to calculate what's going on, but it doesn't really explain what's happening on an atomic level, and this does a better job, okay? So here is our example right here. We're going to start with zinc. It makes zinc and hydrochloric acid makes zinc chloride and hydrogen gas. This is a single replacement reaction, right? My zinc is going to switch places, and then my hydrogen is going to be left alone. So my problem says we start with 5 moles of zinc and 6 moles of hydrochloric acid, hydrogen chloride, and they react, and they want to know how many moles of hydrogen gas are produced. So the first thing we have to do is write our balanced equation so we can figure out what our mole ratios are. We just put that on top of our chart. Before the reaction happens, this is from your problem, okay? Before the reaction happens, I put 5 moles in the beaker and 6 moles of hydrochloric acid in the beaker. And before the reaction happens, there are no products. This is before, so the reaction hasn't happened yet. And now I need to figure out which one is going to be the limiting reagent, and I just do that using my mole ratio. So I cover up one and I check. If I have 5 moles of zinc, how much hydrochloric acid will I need? That's going from moles to moles. That's your mole ratio. So 2 to 1 from the balanced equation, right? 2 and 1. And that means I need 10 moles of hydrochloric acid to completely react with this 5 moles of zinc. So now I have to see, do I have 10 moles? I don't. I only have 6 moles. So this guy is my limiting reactant, and this guy is going to be my excess. Now, my limiting reactant determines the change for all of these guys, okay? So let's see what's happening here. If I have 6 moles of hydrochloric acid, how much hydrogen will I produce? Okay, that's your mole to mole ratio. Here's my given. Get rid of hydrochloric acid, go to hydrogen gas, and it's a 1:2 ratio. That means I'm going to produce, 3 moles of hydrogen gas. Now notice, this is a 1:2 ratio. So here's 2, okay, and here's 1. That means I need half as much. So you can intuitively figure this out. 2 to 1, that's half as much. And sure enough, that's half. And that's what my mole ratio shows me. It's just half. Okay. Now I need to figure out how much zinc I'm going to use up. So I have 6 moles of hydrochloric acid. So how much zinc do I need to get rid of hydrochloric acid? Go to zinc. And again, that's also a 1 to 2 ratio. Here's 2. There's 1. I only need half. So that's going to be 3 moles as well. Now, since this is my limiting reactant, that means I use up all 6 moles. And that's minus because it's going away. Okay. And what I want you to notice is this is a 2 to 1 ratio. This is a 2 to 1 ratio. That means this is a 2 to 1 ratio also. So I would set it up the same way. Hydrochloric would have 2 on the bottom and zinc would have 1 on top. So that's going to be 3 moles as well. So if these coefficients are the same, these numbers in my change should be identical. So without doing all these calculations, you can intuitively figure them out. Now, after, what is left in my beaker when it's all done? Well, I started with 5 moles. I only used 3, so that means I have 2 moles left. I started with 6 moles. I used it up. This is 0. You should always have 0 for your limiting reactant. If it goes negative, you can't use more than what they gave you. That means you picked the wrong one, and you have to double check which one is your actual limiting reactant. Zinc chloride started with 0 and I made 3 moles, so I have a positive 3 moles. And my hydrogen gas, I also have a positive 3 moles. Okay, so now these are all in moles. They could say how many grams of excess reactant do you have, and you would convert moles to grams. They could say how many grams of zinc chloride did you make, or how many grams of hydrogen did you make. And so this chart becomes very helpful, and it becomes a faster way to answer all the limiting reactant problems in one fell swoop. Okay, so take these notes, rewind and watch this as many times as you need to. We're going to do another problem, and we're going to start from grams. Okay, so here's my question. 4.01 grams of nitrogen, actually I changed that to 14 grams of nitrogen and 4.0 grams of hydrogen react. What's the limiting reactant? How many moles of ammonia is produced? How many grams of ammonia is produced? And how many liters of excess reactant is left at standard temperature and pressure? Well, in order to figure out all this stuff, we just use our BCA chart, and the first thing we have to do is we have to convert our grams to moles, because what goes in a BCA chart? Moles only. Say it with me. What goes in a BCA chart? Moles. You put grams here and your answers are all wrong. Okay, it's a common mistake. Usually in class, I have you repeat it every day. What goes in a BCA chart? You got it. It's moles. And then you don't make that mistake, but you're not with me. So I don't know if you're saying it back with me, but you should. So we take our 14 grams of nitrogen. This is N2. 2 nitrogens are 28.02 grams. And for sig figs, I would get 0.5 moles of nitrogen gas. And then my hydrogen, the same. There's 2 hydrogens, so that's 2.02. Okay, that's what that 2 means. So add 2 hydrogens together and convert it to 2 moles. So now I've ID'd my 2 reactants below here. And you can see, because I have 2 reactants, it is a limiting reactant problem. So the first thing we do is we check for which one's the limiting reactant. So I cover up one and I just pick one. It doesn't matter which one you pick. I have 5 moles of nitrogen, so how much hydrogen would I use to completely react with the 0.5 moles of nitrogen? Well, that's my mole to mole ratio. I get rid of nitrogen and I go to hydrogen. Hydrogen has a 3 in front of the balanced equation right there, and nitrogen has a 1. That's a 3 to 1. And so that is going to be 1.5 moles. Does that make sense? Well, I have 1 in my original recipe. It's 1 nitrogen with 3 hydrogen. So I need 3 times the amount of hydrogen, and this is what my mole conversion does. It makes it 3 times that amount, 1.5 moles. Do I have 1.5 moles? I certainly do have 1.5 moles. As a matter of fact, I have 2.0 moles. Okay, so what is going to be my limiting reactant? First of all, I have plenty of this. This means I have excess. Okay, and so this guy is my limiting reactant, and I'm going to use him to calculate all these things. And I am going to set this up and pause my video, and then you'll come back and magically it'll be there. So I've circled my limiting reactant, and I use that to determine how much moles of ammonia will be made. I've already determined how much moles of hydrogen I'm going to use. I'm going to use minus 0.15 moles, and I'm going to make 1 mole of hydrogen, which should be 1.0 mole for sig figs. Okay, and this is my limiting reactant, so I'm going to use it all up, 0.50 moles. Okay, so I have 0 left of my limiting reactant, perfect. My excess reactant, I have 0.50 moles left, and I made 1.0 moles of ammonia. Our problem says how many moles of ammonia are produced. That's 1.0 moles. Then it says how many grams is produced. So now I take that 1.0, and this is for my question 3, and I have 1.0 moles of ammonia. Okay, and I don't want moles of ammonia, I want grams of ammonia. And that would be 17.04 grams per 1 mole. That's the molar mass. That's nitrogen and 3 hydrogens added together, which is going to give me 17.04 grams, but we only need 2 sig figs, so 17 grams of ammonia are produced. Okay, and then it says how many liters of excess reactant is left. So here's my excess reactant. It is a gas. I have 0.5 moles of my excess reactant, which is hydrogen gas. Okay, and I don't want moles. Ooh, sorry about that. And I don't want moles. I want liters of H2 gas. H2 for every 1 mole, that's 22.4 liters. And that is going to 11.2, which is in 2 sig figs, 11 liters of hydrogen gas. Okay, so this was basically your whole problem. I started with grams. I needed to convert it to moles. I figured out what my limiting reactant was, and then I used that limiting reactant to figure out how much hydrogen I used, how much ammonia was produced, and then after I see what's left. I have some excess reactant and I have some product in there, but my question didn't want it in moles. They wanted ammonia in grams, so I converted my ammonia to grams, and they wanted my excess reactant in liters because it's a gas, so I converted that to liters. Okay, and that is the whole problem. So here's our worksheet. I'm going to do a couple with you. This one is about drawing and explaining to you how you can visualize this reaction using the BCA chart. So first we write our balanced equation. That's our recipe. Now that recipe doesn't have anything to do with how much we put in for our problem. Our problem says we put in 4 molecules of hydrogen and 4 molecules of oxygen, and then we want to see what happens after. So this is my oxygen and this is my hydrogen. Let's make that O2. And hydrogen molecules are very, very tiny, so that's why that works. So I need H2O, so 2 H's and an O. So there's 2 H's and 1 O, and I can draw my 2 H's and an O, okay? 2 hydrogens and the other oxygen, 2 hydrogens and the other oxygen, 2 hydrogens and 1 oxygen, 2 hydrogens and 1 oxygen, and I'm out of hydrogen, so I can't make any more water, but I do still have 2 oxygens left over. Okay, so how many molecules of water can be produced? You have 4. Which reactant is in excess? Oxygen. Why? Because it's left over. How many molecules are left over? 2. And remember, we can talk about molecules or we can talk about moles. So we have our balanced equation, which is hydrogen plus oxygen is going to yield water. Before the reaction, what did we put in the beaker? This is directly from my problem. I put in 4 moles or molecules, but remember that's a different thing, but we're going to talk in moles, okay? And before the reaction happened, there was no reaction, so I didn't make any products. And then how did it change? Well, I used all 4 hydrogens, so minus 4 moles of hydrogen. I only used 2 moles of oxygen, and I produced 4 moles of water. Okay, so what is left in my beaker? 0 hydrogens. You notice, I'm just going to put a 0 there. You notice there's no hydrogen atoms left here. There's hydrogens attached to that, but that's a water molecule. Okay, 4 moles to start. I used up 2, so I have 2 molecules or moles left. 1, 2. And then how much water did I make? Well, I started with nothing. I made 4, so I made 4 molecules. Okay, so according to your table, we have 4 moles of water. Oxygen is in excess because it's left over. Okay, and how many molecules of excess reactant are there? There's 2. So this is this picture just redone. Okay, so you can finish this, and you're going to do 2 on your own, and then I am going to do number 3 with you. Okay, so here we have aluminum reacts with iodine to form aluminum iodide. That is going to be a synthesis reaction. Remember, your next test is 3-part exam over 7, 8, and 9. 7 is naming, which you're going to do when we write these things out. Balancing, which you're going to do when we do this, so that's built in, but you will have to remember the types of reactions. So I have aluminum is going to react with iodine, and that is a Brinkelhoff, and it is going to produce aluminum iodide. And how do I know what to write here? Well, that's a +3 and that's a -1. So I have to have a 3 there. And now I have to balance it. So I have a 3 there and a 2 there. Oh, this pencil is annoying. And so I have to have a 2 there. 2 aluminums, 6 iodines, 6 iodines, and I am balanced. And what do I start with? First of all, what goes in a BCA chart? Moles. Do I have moles? Sure, I do. That's great. I don't have to do that much work. So 0.50 moles and 0.72 moles. And before the reaction happens, there are no products. Okay, so now which guy is going to run out? Well, I'm going to pick one. I'm going to pick this guy, and I'm going to see how much iodine I actually need. So I start with 0.5 moles of aluminum, okay? And I don't want aluminum, I want to go to iodine. So my mole ratio is 2 with my aluminum and 3 with my iodine. And then I am going to calculate that. So that would be 1.5 divided by 2. So I have 0.75 moles of iodine I need to react completely with that 0.5 moles. So now I check, do I have 0.75 moles of iodine? I only have 0.72. Do I have enough? No. So this is going to be my limiting reactant, which means this guy is my excess. Okay, so how much am I going to use up I need to use this number to calculate these guys. So we are now going to start with 0.72 moles of iodine, and I need to figure out how many moles of aluminum. So iodine goes on the bottom, aluminum goes on top, and I use my mole ratio, which is a 2-to-3 ratio. So put that in your calculator and let's find out how many moles of aluminum will be eaten up by that iodine. So hopefully you're pausing your video and you're doing this with me, and if you did that, 0.72 moles of iodine will use up 0.48 moles of aluminum. Okay, so I'm going to use up that much, and this is my limiting reactant, so I'm going to use it all up. And then how many moles of aluminum iodide can I make from that? 0.72 moles of iodine. And I'm going from iodine to aluminum iodide, and that is my same ratio. Notice it's still that 2 for aluminum iodide to 3. Now I just did that same work. Notice my coefficients are the same, so when I put that in my calculator, I'm going to get the same number. Again, if your coefficients match, your mole conversions will be the same. So 2 to 2, these numbers should be the same. So now, what is left? Well, I started with 0.5, I used up 0.48, so I have 0.02 moles of aluminum left. I have no iodine left, it ran out, and then I made 0.48 moles of aluminum. So how many moles of the excess reactant will remain? This is my excess, and 0.02 moles of aluminum. Okay, and how many moles of aluminum iodide will be formed? That's my 0.48 moles of aluminum iodide. Okay, and so when you do this worksheet, I want you to make sure you're on the right track. The answers are right here for you.